Good morning, student. Today we are going to discuss about fast transistor logic and transmission gate logic. Last class we discussed about the characteristics of PMOS and NMOS. Today we will see how to use this PMOS and NMOS in the fast transistor logic and transmission gate logic. So in the fast transistor logic, we are using only one type of transistor, either PMOS or PMOS, and each transistor will act as a switch. In most of these designs, they are using only the NMOS because the NMOS is faster than the PMOS because of the mobility of the electrons is faster than the holes. So in most of the places we are using NMOS based design. So this class we are going to deal only with the NMOS based logic. So there are clues there. We can easily design the PTL design using the MOS based. So if I want to design an AND gate function, so I have to connect the transistor series. If I want to design OR gate, I have to connect it parallel. So this is the implementation of simple two input AND gate design. Now VDD is connected to VDD is passed from source to output. Now this will give Y equal to A dot B. Actually, in this design, we are using two transistors to design AND gate, and we can minimize the number of transistors for designing AND gate. That is possible. So in the next circuit, we will see how to design. So this is the alternative way of approach for designing a AND gate. So here I used only one transistor. It will act as a AND gate. If gate of the NMOS is connected to B, and so it gives A dot B. That means for the NMOS want to act as a switch, usually they should be operated in the saturation region. For the saturation region, we have to give high input voltage for the gate. So that is the gate input is nothing but B. When B is 1, it passes the A. So that's why here we are getting A dot B. So in the second circuit, the gate signal is connected to B bar. So the expression for the second circuit is A dot B bar. Next, we will see how to design OR gate using the pass transistor logic. So now this is a circuit for a two input OR gate. Here the output of the first transistor is A, and output of the second transistor is B, and here tied here, so this will give the OR operation. So because these two are in parallel, so it gives A plus B. And next, we can design a 2:1 mux. So the expression for the 2:1 mux is A dot S bar plus B dot S. So first we have to design for A dot S bar. So here the S bar is there, so the control signal should be S bar. In the second term, B dot S, so the gate signal or the control signal is S. Now this will give A dot S bar and this will give B dot S, and these are connected. So the final result will be A dot S bar plus B dot S. Next we will see how to design two input XOR gate. Everyone knows that the expression of the two input XOR gate. Here I have taken X is the output and B and C are the input. So B XOR C is nothing but B bar dot C plus B dot C bar. Okay. So first we will design this B bar dot C. So B bar dot C is this will give the B bar dot C, and this transistor will give B C bar. And if we join these two things, and finally we will get X. So now X is nothing but B bar C plus B dot C bar. Okay. Now the same logic we can use it for 3 input XOR gate. So we can extend from 2 input to 3 input XOR gate. So next we will see 3 input XOR gate design. So now this is a 3 input XOR gate design. So usually the sum output of the full adder is AX or BX or C. Okay, so sometimes they may ask draw the PTL logic diagram for sum output of the full adder. Now both are same. So what we have to do first, we have to expand that. Now we can take it as this B XOR C is a X. So if you have A XOR X means, so if you expand this, A bar dot X bar plus A dot X bar. So if you replace X by B XOR C, you will get this expansion. So why we have designed like this means, already we designed for XOR. Now X gives XOR, B XOR C, and Y give B XOR C whole bar, that is uh, B X not C. So these two gates give XNOR output, and these two gate gives XOR output. So finally what we have to do, we have to do the AND operation. So with the A bar, so now this X and these are connected series, and here the XNOR and A are connected series, here Y and A XNOR is connected series, and finally there is an OR option, so we have to connect these two things. Now it will give 3 input XOR gate. So like we can design any type of gates using this concept. Next we will see how to design compound gates. So compound gates is nothing but some expression is given. From for the given expression we have to design the circuit using PTL logic. Okay. So now this is a simple example for the compound gate. So Z equal to A bar dot B plus CD. So first we will take this B plus CD. So we are having OR operation. So B, C and D are connected in parallel, and this group is AND with A bar. So AND means now these two groups should be connected series. So the final result we will get A bar of B plus C plus D. Okay. The problem in the transistor logic is when the condition is satisfied, that is the switches are closed, it will give the correct output. The output may be degraded output. If it is 0, we will get good 0. If it is 1, we will get degraded 1. And one more thing, when the condition is failed, for example, here A bar is 1 and B is 0, C is 0 and D is 0. So that means this switch is on, the remaining these three switches are off. So usually when the if the condition is failed, it should give 0. Am I correct? So this condition is satisfied, Z should 1. If the condition is failed, Z should 0. So here we are expecting Z should 0, but here Z won't be 0. So it will retain a previous state, it retains a previous value, that is the output doesn't 0. So this is the main drawback in the PTL logic. So it requires some additional circuitry to make it to proper operation. So that's why the PTL is not suitable for all the types of circuits. Okay. So next we will see the transmission gate logic. The TG logic. In the PTL we used one transistor as a switch, but here we have to use one pair of transistor act as a switch. Okay. So to create one TG cell, one NMOS and one PMOS are needed. Both NMOS and PMOS are connected parallel. Okay, so this is very important point. So both are connected in parallel. And then another important point is the gate signal of PMOS is complement of gate signal of NMOS. So we should not give the same input signal for the gate of PMOS and NMOS, because when the gate of NMOS is connected to VDD, the switch is on, but the gate of PMOS is connected to ground, the switch is on. So we have to give the complement inputs. So this is very very important term. So there are using different symbol for TG. So here A is the input signal, B is the output signal, G is the gate of NMOS, and GB is the gate of PMOS. Actually, GB means uh, G bar, that is complement of G. So that's why they name it as the GB here. Okay. So hereafter we are using only the first symbol. Okay. So please take care of these things. Now first we will see how to design a one variable circuit. Suppose if I want to design S bar, so I have to make like this. So for better understanding, you can take the reference is NMOS of the gate. So if the NMOS of gate is here S bar, so it will give S bar because we are passing data VDD. So VDD is logically 1. So 1 dot S bar we will get S bar. Suppose if we interchange S bar as S and the function it will give z equal to S. And here one more thing we should keep it in mind. So here the complement of NMOS and PMOS, the gate of NMOS and PMOS are complements. Okay, so these things we should keep it in your mind. Next, we will see how to design two-input AND gate using transmission gate. So we know the expression of the AND gate is A dot B. A is the data we are processing, and B is the the gate of NMOS should be B. So the gate of PMOS is B bar. So this is the easy ways design, but if you compare to PTL, it needs more number of transistors, usually 2 times. So next we will see how to design 2-input OR gate using transmission gate line. So it's similar to the pass transistor logic. The only difference in the pass transistor logic, we have to use only NMOS, but here we have to use pair of MOS, one NMOS and one PMOS. And one more thing, if the gate of NMOS is connected to A and the gate of PMOS should be connected to A bar. So that's it. So the remaining things are same. Okay. So this will, the first TG will give A, the second TG give B, and both are connected. So the final result will be A plus B. Okay. So if I want to design 2:1 MUX, this is the circuit further. If you look at the previous circuit, we need only 2 transmission gate to design OR gate. Okay. And 1 transmission gate is required to AND gate. If you look at this one, for designing 2:1 MUX, I need only 2 transmission gate and 2 transistor. So S bar cannot be designed with the TG, so we have to use CMOS logic to design the S bar. So the CMOS gates, one inverter, one CMOS inverter needs 2 transistor, one PMOS and one NMOS. And again, here we need 2 TGs are there. So totally I need only 6 transistor. So by using the 6 transistor, I can design 2:1 MUX. There is another approach. First, we write the expression in terms of gate. Then each gate is replaced by the transistor circuit. Suppose if I replace the transistor by gate level, I need more number of transistor. For example, for the designing a MUX, I need 4 gates, 1 NOT gate, 2 AND gate, and 1 OR gate I require. Okay. So I can design NOT gate in 2 transistor, and AND gate need 1 TG, that is 2 transistor, and again there are 2 AND gates, so 4 transistors are required. An OR gate required 2 Tg, so 4 transistors. So totally I need 10 transistor. Instead of the going gate level to transistor level, if we go for directly transistor level, we can minimize the number of transistor. So here I need only the 6 transistor. So this point we should keep it in your mind. So why the design is going to transistor level diagram directly than gate level to transistor level. Okay. So next we will see how to design XOR gate using PG. So now this is the circuit for XOR gate. So output of the first transistor is A bar B, and output of the second transistor is a second TG is AB bar. Okay. So if you add these two things, I'll get the result value. Okay. So far we have discussed only about the combination circuit. So the TG can be used in sequential circuit also. So first we will take the D latch. So this is the internal diagram of D latch. So the D latch required one 2:1 mux, two NOT gates. Okay, actually the output is taken here, and input, the D is connected to one input and Q is connected to 0 input. So this feedback is required. When the clock is negative, it should retain this its previous state value. For that purpose only we are using this feedback path. If this feedback path is absent, we cannot retain the previous state value. That is, when the clock is low, we cannot predict our output value. So for this purpose only, we are using this back-to-back inverter. Okay. And positive latch. So for better understanding, you can consider there are two switches. So this is the data switch and this is the feedback path switch. So the purpose of the data switch, it should transfer the new data, and the feedback switch is it retain the previous data. Okay. So the positive delatch means the data switch should be closed when clock equal to 1. So here you can see this. When clock equal to 1, it gets the new data. When clock equal to 0, it retains the previous state. So from the diagram itself, you can easily understand why it's called positive delatch. So the positive delatch means when clock equal to 1, it gets the data. When clock equal to 0, it retains the previous state value. Okay. So already we discussed we can design a 2:1 mux using two transmission gates. Am I correct? So here we used only two transmission gate to design a 2:1 mux. The same type of circuit is used here. So there are two switches. Each switch need one TG cell. So this is one TG cell and this is one another TG cell. So now how we can use this TG means already I told you, when clock, this is the data switch and this is a feedback switch. When clock equal to 1, this should be on. That means so the gate of NMOS should be connected to clock. So the gate of PMOS is connected to clock bar, and this feedback switch is closed when clock equal to 0. So the gate of NMOS is connected to clock bar here. If it is clock bar here, then the gate of PMOS should be connected to clock. Okay. So this thing, please keep it in your mind. This switch is closed when clock equal to 1, and this switch is closed when clock equal to 0. Okay. So this is the symbol for this. This is the symbol. Why we are using positive clock means it's a positive delatch. Okay. So when clock equal to 1, it gets the data. So that's why we are using the positive clock. Okay. And this is the waveform for this. So when clock changes from 0 to 1, and this whole period it gets the data. See here initially D, actually D changes here, but the Q the flip-flop gets the data, the change of D only from this. So it will this half of the cycle, that is during the clock I, what are the changes in the D? It accept all these things. That is it accept the D continuously for the half of the cycle. Okay. Even if there is any unwanted glitches, the flip flop gives the same glitches also. So this is the drawback in the delatch circuit. So this is a positive delatch. So next we will see the negative delatch. Okay. So negative delatch means the data switch should be closed when clock equal to 0 and feedback switch is closed when clock equal to 1. Okay. So that's why this is the data switch and this is the feedback switch. So the gate of NMOS of the data switch is connected to clock bar, because when clock equal to 0 it should get the data. And here the gate of NMOS of feedback switch is connected to clock. That is when clock equal to 1 it should retain the previous state value. So this is the difference between the positive delatch and negative delatch. The positive delatch it accepts the whole off cycle when clock equal to 5. The negative delatch it accepts the data for the whole off cycle when clock equal to 0. Okay. So once if we know the positive delatch and negative delatch, we can easily build the positive HD flip-flop, positive H trigger D flip-flop. Now we will see how to design positive H trigger D flip-flop. Okay. So the difference between the latch and the flip-flop is the latch accept the data for the half of the whole cycle, but the flip-flop accept the data only during the transition, either the rising edge or falling edge. If it accept the data only during the rising edge, it's called positive edge trigger flip-flop. If it accept the data only during the falling edge, then it's called negative edge trigger flip-flop. Okay. So there are two types of edge trigger flip-flop in D. Okay. So first we will see the positive edge trigger flip-flop. Now this is the block diagram for this. This is the symbol of the positive edge trigger flip-flop. So D is input, Q is output, and clock we have to do. So this is the block diagram of that. This is the symbol, and this is the block diagram of that, and this is the internal diagram of that. Okay. So if you look at the block diagram, there are two latches there. So the first latch is connected to clock bar. The second latch is connected to clock. So if it is connected to clock, now this is positive latch. And if it is connected to clock bar, then it is called negative latch. Okay. So what I am going to say here, for positive edge trigger flip-flop, the first stage is negative latch, the second stage is positive latch. Okay. So already we discussed the negative latch, and then this is the first latch. This is the negative latch. In the negative latch, the data switch should be on when clock equal to 0, and the feedback switch should be on when the clock equal to 1. So this is negative latch. And for the positive latch, the data should be closed when clock equal to 1, and here the data switch should be on when clock equal to 0. So that's all. So if we understand this block diagram, we can draw this internal diagram yourself. Okay. So this is for positive edge trigger flip-flop. So next we will see how it's going to operate. Okay. So when clock equal to 0, what will happen? It gets the data. Am I correct? So it will be stored here. Okay. So during the clock equal to 0, it retains a previous value. Okay. Because here the feedback switch is closed, it gets the data, but this is not processed to flip-flop. Okay. because this switch is open, so there is no connection between D and Q. So it will retain the previous output. Okay. When clock equal to 1, what happened? This switch is closed and this switch is open. So at the moment, at the transition, the data, what the data is available, that is passes through this switch. So here it gets the D value. Okay. So that's why I told you the flip-flop accepts accepts the inputs only during the transition time. Okay. Here it accepts this input only during the rising edge. When clock equal to 1, what happens? The moment the clock changes from 0 to 1, this switch is open, at the same time this switch is closed. So it gets the data during the transition time. Okay. Now this is the output. Now this is the clock value. So here the clock changes. So this is a rising edge. So it gets the data only at the rising edge. Now what is the D value? D is 1. So the Q also changes to 1. So it will retain the same value until the next clock rising edge arrives. So this is the next clock rising edge, and again we check the data value. So here next clock rising edge D is 0. So now what happened? Now the Q goes to 0. Okay. So this is the waveform of positive edge trigger flip-flop. Okay. So the last one is a negative edge trigger flip-flop, D flip-flop. So from the diagram itself, from the symbol itself, you can understand. That is, so the clock bar is given. So the clock bar is better you take it as this is the here the clock bar means the second stage latch is a negative latch. So the first stage latch is a positive latch. Then you can draw the internal diagram yourself. Okay. So now we will see what is the need of CMOS logic. Actually, the main problem in the PTL logic and transmission gate logic is when the condition is satisfied, we are getting the correct output. Suppose if the condition is not satisfied, that means if there is no path for the output from the input means the output won't be zero. It has some value. So we cannot predict that output. So when we are using the millions and billions of the transistor, we cannot use this type of logic because in digital circuit the output should have only two logic level 0 and 1. We should not have any intermediate value. But if we use a pass transistor and transmission gate, I am getting this value. I am getting some intermediate outputs. So to avoid these things, we are going for the CMOS because CMOS give only two values, either 0 or 1. Okay, 0 or VDD in analog. So that's why we are going for the CMOS. So first we will see where we have to connect the PMOS and NMOS. So in the transmission gate we are using pass transistor. We are using PMOS and NMOS, but they are connected parallel. But in the CMOS, the PMOS and NMOS are not connected in parallel. Okay, so here the PMOS and NMOS is a connector one after another. So first PMOS, then PMOS. Okay, so first we will take a simple example. Before we are moving to CMOS, we will try to this one. So here the NMOS is connected to VDD and PMOS is connected to ground. Now if you look at this diagram, NMOS is connected to VDD and PMOS is connected to ground. Actually the NMOS has good 0 and bad 1 property. That means when this NMOS is on, this NMOS is connected to VDD. Now output goes to 1. So it's a degraded one because the property of the NMOS. And again, here the PMOS is connected to ground. So when this PMOS is on, now this 0 is connected to Y. Actually, the PMOS has good 1 and bad 0. So that means we will get degraded output. So in both cases, the 1 and 0, we are getting degraded outputs. So that's why this is called bad buffer. When A is 1, output also 1. When A is 0, output also 0. But these 1 and 0s are degraded output. So we are not interested in the degraded outputs. Then how to connect the PMOS and NMOS. So we will see. So in this diagram, here you can see, now this is CMOS logic. CMOS means complementary metal oxide semiconductor. So from the name itself, we can understand how the circuit is going to work. So it's working on the complementary manner. That is, if my input is 0, output will be 1. My input is 1, output will be 0. Okay, so that's why the name came complementary. Okay, the output is complementary of input. And here the PMOS is connected to VDD because the PMOS has good one property. So the PMOS is connected to VDD and NMOS is connected to ground because NMOS has good 0 property. When A is 1, NMOS is on and NMOS is connected to ground. Now 0 will be passed. So that means now Y equal to 0. When input is A is 1 and Y is 0. Suppose if A is 0, PMOS is on and PMOS is connected to VDD and this VDD is passed to this Y. Now output goes to Y, that is Y is 1. So when A is 0, Y is 1. When A is 1 and Y is 0. So it acts as like a inverter. Okay? So usually we are using the inverter symbol for CMOS. Okay. So this logic we can extend for any number of size. Okay, it's not only for one weight, we can extend this one also. So for extend, so there is a standard method is there. So PMOSs are called pull-up networks because when PMOSs are on, output goes to 1, so it's called pull-up network. Output is pulled up. When NMOSs are on, output goes to 0, that is pulled down. Okay, so this is called pull-up network and this is called pull-down network. Okay, next we will see how to design a 2-input NAND gate using CMOS. So this is a truth table of the NAND gate. So it's a 2-input, so AB are inputs. So there are 4 combinations 0 0 0 1 1 0 1 1. So why we know this? So for the first 3 combination outputs are 1. The last combination output is 0. So if output should be 1, then pull-up networks are on. If output is 0 and pull-down network is on. So we have to design such that. Okay. So that is, I'll repeat it again. When output is 1 means pull-up network should be on. When output is 0, pull-down network should be on. So how to make this one? If we connect PMOS as a parallel, am I correct? So we will get this one. And if we connect NMOS as a series, and we will get this one. So that's why they connected here. So PMOSs are connected parallel and the NMOSs are connected series. Now in the shortcut technique, if we have the dot under the bar, okay, the corresponding expressions PMOSs are connected parallel and NMOSs are connected series. Okay. Now here you can see this. So design a 3-input NAND gate. Now what is this expression? A dot B dot C whole bar. So if you have the dot operation, what is the shortcut technique? PMOSs must be connected parallel. If PMOSs are connected parallel, then NMOSs should be series. So that's why we have drawn like this. Okay. So next we will see how to design 3-input NOR gate. So this is 3-input NOR gate. So the expression is A plus B plus C whole bar. So already we discussed the shortcut for dot under the bar. Suppose if you have plus under the bar, the PMOSs should be series and the corresponding NMOSs of a CMOS are parallel. Okay, so I'll repeat it again. If we have the plus under the bar, then PMOSs must be series and the NMOSs must be parallel. Okay. Next we will see how to design compound gates using CMOS logic. Okay. So this is the expression. So the given expression is A plus B plus C dot D whole bar. So first we will take this one. So A plus B plus C under the bar. So if A plus B plus C under the bar means the PMOSs are in series, the corresponding NMOS of the CMOS is parallel. So then D, D, and these two groups are dot operation. So dot operation means these two groups PMOSs are connected parallel. So that's why we connected like this. So ABC and D, these two groups are parallel. The corresponding NMOSs are in series. Am I correct? Then finally we have to add these two things. We will get the final diagram. So this is the compound gate realization using CMOS. Okay. Any doubts in this? How to do this? So next we will see how to implement the two input XOR gate using CMOS logic. So usually the CMOS logic is applicable only when we have the whole bar. Suppose if we don't have the whole bar, we have to make the circuit such that we have the whole bar. Or in some cases it is not possible to make a whole bar. Then what we have to do? We have to design with whole bar, and finally we have to connect one NOR gate. Then we will get the correct expression. But here A XOR B, actually the XOR does not have any whole bar. But what we can do, we can write the XOR gate as A XOR B whole bar. Now both are logically same. So here I have the whole bar. Now I can easily apply the CMOS logic. Okay. So what is the expression for A XOR B? So the expression of A XOR B is A bar B bar plus AB. Am I correct? So A bar B bar plus AB. So A bar B bar should be connected parallel in the PMOS. The corresponding A bar B bar must be connected series. Then AB should be connected parallel and the corresponding NMOS must be connected series. And A bar B bar plus AB. So plus means the PMOSs are connected series and the NMOSs are connected parallel. Okay. So this is the idea to design XOR gate. Actually we can design the XOR gate in many ways. So this is one of the way. Okay. Thank you.